Hello everyone, this is Dr. Meyer here with a video for you on prime form, a final step in set theory analysis that will help us compare pitch class sets to one another. If you haven't watched the videos on normal order or transpositional and inversional equivalence, I suggest starting there first. There are some links in the description. Let's get started. So what is prime form? It feels just like we're adding another label. At this very basic level, set theory does involve naming a lot of things, but also finding a precise and accurate way to describe musical objects. So while naming things can be sort of a low-level analytical act, it's very helpful to gain insight into how a piece of music was constructed. Pitch class sets have to share the same collection of intervals in order to be transpositionally or inversionally related to some other pitch class set. This is most easily grasped by remembering that all major and minor triads have the same interval content, that major third, minor third, and perfect fifth. Major triads are transpositionally related to one another, while major and minor triads are inversionally related to one another. So like A major and A minor, we can see that this pizza-shaped triangle should be flipped from A minor in order to create A major, because they have the same intervals inside. When sets have the same intervallic content, we can label transpositional and inversional relationships between them, so as we call them Tn or Tn of I. All pitch class sets that are transpositionally and inversionally related belong to the same set class. This is a collection of equivalent forms of the same set, and they are represented by what we're going to call prime form, or they have the same prime form. So how can we put a set into prime form? First, let's begin with normal order. So let's take the set 8, 4, 3, 1 and put it into normal order. So that's 1, 3, 4, 8. We're going to assign 0 to the first pitch class in the set and renumber the rest of the set using the AIS to produce this transposition. So 1, 3, 4, 8 by T11 gives us 0, 2, 3, 7. Or using the AIS of 2, 1, 4, we can just add those intervals to everything starting on 0 and come up with the same result. That is 0, 2, 3, 7. To make sure we have the smallest packing to the left, we'll check the inversion of this set by inverting around 0 and transposing to 0. So we can invert 0, 2, 3, 7 about 0 using our rainbow and get 5, 9, 10, 0. Transposing this to 0, we get 0, 4, 5, 7 with an AIS of 4, 1, 3. So now we're going to compare both of our sets, see which one is most tightly packed to the left. We can see that our first result with the AIS of 2, 1, 4 has that tight packing to the left. So we're going to take that result, put it in parentheses to show that we have found our prime form. Also, notice that we've removed the commas from between the numbers, so we have parentheses 0, 2, 3, 7, and parentheses, that's our prime form. So this is kind of the long way of figuring out prime form. So I'm going to show you one more way that might be a little bit easier. You can also use the clock face to observe this set in a more graphic way. So let's take the set 5, 9, 10, 0. This is already in normal order. Here are two clock faces with that set mapped onto them. If we start reading the set clockwise and reassigning intervals starting at 0, we can see that we'll have 0, 4, 5, 7 for our prime form. If we start reading the set anti-clockwise and reassign the intervals, we get 0, 2, 3, 7. Comparing the two, the interval from 0 to 2 is smaller than the interval from 0 to 4, so we can choose the circle on the right for our prime form, that being 0, 2, 3, 7. But didn't our first set have a prime form of 0, 2, 3, 7? Yes! In fact, we have found that 1, 3, 4, 8 and 5, 9, 10, 0 were both having prime form of 0, 2, 3, 7. If we check out their AISs, we can see that they are inversionally related. So check out the rainbow. We can see they are T1 of I related. Therefore, sets with the same prime form are going to be transpositionally or inversionally related. Now it's your turn to practice. This example from Schoenberg's suite for piano in the prelude movement has two segmented motives, one in blue and one in green. I've linked an audio file in the description. Find the normal order of each of the motives and see if they share the same prime form. Remember, you may have to read from the right in order to get the smallest packing for prime form. Pause the video now, grab a pen and paper, and take your time. You should have found the blue segment to be 1, 4, 5, 7 in normal order, and the green segment to be 7, 10, 11, 1 in normal order. Checking out the AIS, we can see they are transpositions of one another. And check out the score. Those two motives are definitely contours of one another. Did you find them to be T6 related? Using the AIS, we have to read from the right to get the prime form of 0, 2, 3, 6. If you got 0, 3, 4, 6, you read from the left and you do not have the closest packing to the left, because 0 to 3 is larger than 0 to 2. Be sure to check that final step before committing to a prime form. One more practice example from another movement of Schoenberg's suite for piano, the Gavotte. There's a link in the description for the audio. Same as before, find the normal order for each of the segments and convert each to prime form. Pause the video, grab your pen, take your time. You should have found the blue segment to be 1, 4, 5, 7 in normal order. That looks familiar. It's almost as if Schoenberg is using this motivic set in multiple movements of this work. Hint, hint, he definitely is. The green set is 7, 9, 10, 1 in normal order. By checking out the AIS, we can see they are inverses of one another and are therefore inversionally related. You can even see on the score of how they look like mirror images of one another. Did you find them to be T2 of I related? With that relationship, you should have found the prime form to be 0, 2, 3, 6, where you have to read from the right on the blue segment. So we're noticing that Schoenberg is using a lot of different motives with the same prime form in multiple movements of this piano work. There's lots to discuss, and making these observations is the first step to understanding how post-tonal music is constructed. How cool is that? So here's what we learned in this video. Prime form is the most common way to identify all subsets of a pitch class set with one unique label to describe their intervallic content. To find that prime form, start with normal order, transpose to 0, and find which reading will result in the most tightly packed to the left, whether you have to read it from the left or from the right. You can do that extra step and examine the inversion of your normal order too, just to make sure you're checking all the intervals. Or you can use the clock face to visualize the set in a different way. Remember, sets that share the same prime form are going to be transpositionally or inversionally equivalent. Not all sets will share the same prime form. But that's the fun of analyzing this music, finding the patterns and understanding the process. Prime form is actually a quite useful label. There are only a small number of possibilities based on the pitch class sets. For example, there are 220 distinct 3-note chords, but only 12 different 3-note chord prime forms. Talk about continuity for motivic options. That's super cool. We are going to continue practicing prime form and set analysis in class, so don't worry, more practice coming. That's all for now. Thanks for watching.